Welcome to GATE class. So today we will solve some problems related to Fourier series and Fourier transform. So an input signal with alpha greater than 0 is applied to a causal filter the impulse response of which is a exponential minus alpha t. Determine the filter output and also sketch it as a function of time, and label the important points So let us discuss this problem. So the impulse response ht is given as a exponential minus alpha t. So this is a LTI system. So in LTI system we have impulse response st, xt is input and this is yt. So xt is provided, xt is given as a exponential minus alpha t and ht is also given, it is equals to a exponential minus alpha t. So both xt and st is given. Now what is xf? That is the Fourier transform of xt, and it is equals to a divided by alpha plus j 2 pi f. Please check this. We have already solved this type of problem. And hf is given as Fourier transform of ht. hf is transfer function and that is Fourier transform of st, and it is equals to a divided by alpha plus j 2 pi f. And this is Fourier transform of impulse response ht, and this is also called the transfer function. This is also called the system transfer function. So this output yf is product of xf multiplied by hf, and putting the value of xf and hf, so we can use that expression. xf is a divided by alpha plus j 2 pi f multiplied by hf, that is a divided by alpha plus j 2 pi f. So what we will get? yf. So yf we will get as a square divided by alpha plus j 2 pi f whole square. So yt we will get as a square and this is t e raised to the power minus alpha t into ut. Basically we have used that property that Fourier transform of e raised to the power minus alpha t into ut is 1 divided by alpha plus j 2 pi f whole square. Then if we find out the Fourier transform of t e raised to the power minus alpha t into ut, then it is equals to here this is simply L 1 divided by alpha plus j 2 pi f, not whole square. So the Fourier transform of t e raised to the power minus alpha t into ut is equals to, so it is equals to it is simply equals to 1 divided by alpha plus j 2 pi f whole square. So yt is equals to a square t e raised to the power minus alpha t into ut. Here we have written that a square multiplied by 1 divided by alpha plus j 2 pi f whole square. Now this yt, we need to find out the maximum value of yt. For sketching, for plot, what we need to find out? We need to find out the maximum value of yt. So to find out the maximum value of yt, we can differentiate yt with respect to t. So dyt divided by dt is equals to a square t e raised to the power minus alpha t into minus alpha plus a square e raised to the power minus alpha t into 1, and that is equals to 0. So finally what we are getting, solving this expression, we are getting e raised to the power minus alpha t 1 minus alpha t equals to 0. So that t is equals to 1 divided by alpha. So this is t maximum, tm, that it is tm, and at this value of t we are getting the maximum value of yt. So what is maximum value of yt? So y maximum at tm is equal to 1 divided by alpha is a square divided by ae. This is the maximum value of y we are getting at tm is equal to 1 divided by alpha. So let us plot this graph. So the graph is like this. We have at y-axis we have yt, at x-axis we have t, and the graph is like this. So at t is equals to tm, and that is equals to 1 divided by alpha. The value of yt is y max, and this y max is equals to a square divided by alpha e. This is the maximum value. This is 0, and it is decreasing time. So this is the sketch of output yt. Let us solve another problem. So the problem is a signal Vt is equals to 1 plus mt cos omega ct is detected using the square law detector, having the characteristics v naught is equals to vt square. If the Fourier transform if the Fourier transform of MT is constant MF extending from minus Fm to plus Fm, sketch the Fourier transform of V naught. Sketch the Fourier transform. This is V naught. This is V naught t. So sketch the Fourier transform of V naught t in the frequency range minus Fm is less than F less than plus Fm. So we can solve this problem. So we have a square law detector. This is a square law detector. This is input Vt and this is output V naught t, and that is equals to V square t. So V is equals to 1 plus mt cos omega ct square, because it is given that it is basically V naught t is V square t. So Vt is given, Vt is equals to 1 plus mt cos omega ct, that is equals to V square t. So this is V naught t. So V naught t is equals to, just we are going to solve this expression. So it is equal to 1 plus m square t plus 2 into mt cos square omega ct, and that is equals to 1 plus m square t plus 2mt 1 by 2 cos 2 omega ct. So what we are getting finally is V naught t is equals to 1 divided by 2 plus 1 divided by 2 cos 2 omega ct plus 1 by 2 m square t plus mt plus 1 by 2 cos 2 omega ct plus 1 by 2 cos 2 omega ct multiplied by m square t plus 1 by 2 cos 2 omega ct multiplied by 2 mt. Now if we just see the expression, because that mt is the Fourier transform of mt is mf, and that is limited between minus fm to plus fm. So this is mf, that is Fourier transform of mt. So after passing it through the low pass filter, so after passing the V naught t to low pass filter, because we have to ultimately extract that mt. So after passing through that low pass filter, we get that output, that is V01T, let it is V01T, that is the output of the low pass filter, output of low pass filter. That output is equals to 0.50 plus only low frequency component it will extract. This is the output we are getting. Now this is the final output, because that frequency components related to FC and 2FC, it will extract out from the low pass filter. So this is the final output we are getting. And the Fourier transform, if we take the Fourier transform of this, so the Fourier transform we are getting is a DC component, then we have M, this is minus Fm, this is plus Fm, then we have minus 2Fm plus 2Fm. These frequency components we are going to get after passing through the low pass filter. New topic is LTI systems. LTI systems characterized by differential equations. So let us discuss this. So basically that linear constant coefficient differential model, if you remember that we have studied in case of Laplace transform, it is summation k is equal to 0 to capital N ak d raised to the power means k derivative of yt it is equals to summation k is equals to 1 to capital M, it is bk, then we have k derivative of input xt. So we have condition that the value of capital M is less than or equal to n. So if we take the Fourier transform on both sides, so what we will get, y omega is summation k is equals to 0 to capital N ak j omega raised to the power k is equals to x omega summation k is equals to 0 to capital M bk j omega raised to the power k. So we have kept y omega and x omega outside this summation because it is not varying with respect to this variable k, small k. So that h omega, that is the transfer function of the system, that is transfer function of the system. So this h omega is equals to y omega divided by x omega, and that is equals to summation k is equals to 0 to capital M bk j omega raised to the power k divided by summation k is equals to 0 to capital N ak j omega raised to the power k. So what is that expression tells us that, so basically this h omega is equals to y omega divided by x omega is a rational function of omega, is a rational function of omega. So h omega is equals to hs when we have s is equals to j omega, and that is equals to hj omega. Let us discuss some important terms that we are going to use again and again in case of analysis of LTI system. So we have correlation and spectral density. So we have correlation and spectral density. So for energy signal, we have autocorrelation function. So it is Rx tau, that is autocorrelation function. It is equals to minus infinity to plus infinity axt x conjugate t minus tau d tau. So this expression provides similarity between ext and ext minus tau. What is xt? Xt is the signal. Xt minus tau is delayed signal with delay tau. So putting tau is equals to 0, we get Rx0 is equals to minus infinity to plus infinity modulus of xt square dt. That is energy of the signal xt. That is nothing but energy of the signal ext. So this is the relation between the autocorrelation function and energy. So when we have delay tau is equals to 0, this Rx0 is equals to energy of the signal. Let us discuss the energy spectral density. Let us discuss the energy spectral density. So it is called ESD. In short, it is it can be written as ESD, that is energy spectral density. So we have energy spectral density of input side, the input signal xt. It is denoted as psi xf. It is equals to modulus of xf whole square. That is energy spectral density of xt. And what is xf? xf is Fourier transform of ext. So modulus of xf is the amplitude spectrum of xt. Is the amplitude spectrum of xt. So what is the relation between energy spectral density and autocorrelation function? So this relation is provided by Wiener-Khinchin relations. So we have we have Wiener-Khinchin relations for energy signals. So according to this relation, the energy spectral density psi xf is basically the Fourier transform of Rx tau, that is equals to minus infinity to plus infinity Rx tau e raised to the power minus j 2 pi ft 2 pi f. So it is Rx tau exponential minus j 2 pi f tau into d tau. So this is the relation between energy spectral density and autocorrelation function. And what is Rx tau? So Rx tau is inverse Fourier transform of psi xf, and it can be find out as Rx tau is equals to minus infinity to plus infinity psi xf exponential j 2 pi f tau into df, because we are going to find out the inverse Fourier transform of psi xf. So please note that, please note however that the Fourier transform note however that the Fourier transformation is performed with respect to the adjustable lag tau. So Rx tau is basically, if we find out the Fourier transform, that is autocorrelation function Rx tau, if we find out the Fourier transform, that is equals to psi xf, and this is called the Wiener-Khinchin relations for energy signals. So for tau is equals to 0, we have Rx 0, that is equals to minus infinity to plus infinity psi xf exponential j 2 pi f into 0 df, that is equals to minus infinity to plus infinity psi xf into df. So this is basically the area of that is ESD is equals to Rx 0. So another relation for that is that if we find out Rx 0, and that is equals to area of the energy spectral density. This is area of ESD. So what is psi xf? So psi xf is minus infinity to plus infinity Rx tau e raised to the exponential raised to the power minus j 2 pi f tau into d tau. Now if we put f is equals to 0, what we get, psi x 0 is equals to minus infinity to plus infinity Rx tau t tau, that is autocorrelation function, that is area of autocorrelation function. So psi x0 is total integration of Rx tau from tau is equals to minus infinity to plus infinity. These two relations are very important. So it states that, if we just analyze that, it states that the total area under the curve total area under the curve of the complex valued the total area under the curve of complex valued autocorrelation function of a complex valued energy signal is equal to the real valued energy spectral density psi x0 at zero frequency, that is f is equals to 0. Let us find out the autocorrelation function of sync pulse. Autocorrelation function of sync pulse. So that xt is equals to a sine c to omega t. So this is sync pulse. So the Fourier transform of this is the Fourier transform of ext is xf, and that is equals to a divided by 2 omega rect f divided by 2 omega. So since the rectangular function rect f divided by 2 omega is unaffected by squaring the energy spectral density of ext is therefore psi xf is equals to a divided by 2 omega square rect f divided by 2 omega. So taking the Fourier transform, because why we are getting this, because Rect f divided by 2 omega is if we basically with that rect f divided by 2 omega square is equals to rect f divided by 2 omega. There is no harm in writing like this because squaring will not affect that area. So now taking the inverse Fourier transform, of psi xf, this psi xf, we find that the autocorrelation function of sync pulse a sine 2 omega t is given by Rx tau, and that is equals to a square divided by 2 omega w sync 2wt. So what is that? It means that which has a similar waveform as plotted as a function of lag tau as the sync pulse itself. Now we can find out that effect of filtering on energy spectral density. So let us find out the effect of filtering on energy spectral density. Effect of filtering on energy spectral density. Let us find out the effect. Now let us suppose that the energy signal xt, let us take an energy signal xt and suppose that the energy signal xt is passed through a linear time invariant system of transfer function hf, So, and it yields the signal, so it yielding the output signal yt. Then Fourier transform of the output yt is related to the Fourier transform of input ext as follows. Yf is equals to hf multiplied by xf. So taking the squared amplitude taking the squared amplitudes on both sides of the equation, we readily get psi xf is equals to modulus of hf square. So this is psi yf. This is psi yf is equals to modulus of hf square into psi xf. So what is psi xf? That is equals to modulus of xf whole square. What is psi yf? That is equals to modulus of yf whole square. So we have this definition of both this energy spectral density of our input and output, and this is basically the squared spectrum of this squared absolute spectrum of transfer function. So it states that it states that when an energy signal when an energy signal is transmitted through a linear time invariant filter, the energy spectral density of the resulting output signal equals the energy spectral density of input multiplied by the squared amplitude response of the filter. Now we have another very important term that we are going to study is cross correlation of energy signal. Cross correlation function of energy signals. So let us discuss this cross correlation function of energy signals. So the autocorrelation function provides, so basically the autocorrelation function provides a measure of the similarity between a signal and its own delayed version. So in a similar way, we may use the cross correlation function. We may use the cross correlation function as a measure of as a measure of similarity as a measure of similarity between one signal and the time delayed version of second signal. So let xt and yt denotes a pair of complex valued energy signals. The cross correlation function of this pairs of signals is defined as rxy tau is equals to minus infinity to plus infinity xty conjugate t minus tau dt. So we see that two signals ext and yt are somewhat similar, then the cross correlation function rxy tau will be finite over some range of tau, thereby the similarity or coherence between them. So the signal xt and yt, the signals xt and yt are said to be orthogonal, over the time interval if rxy 0 is 0, that is minus infinity to plus infinity ext y conjugate t dt is equals to 0. Let us solve some problems related to this Fourier series and Fourier transform. So the problem is over a period that is only one period from 0 to capital T, each of the two periodic waveforms W1 and W2 are shown in figure below. So we have figure W1, that is from this is 0 and this is 0, this is t by 2, then this is t, so it is 1.0, it is minus 1.0. This is W1 and another waveform is W2. So this is somewhat triangular type. We have one triangular, upper and lower. So 0, this is plus 1, this is minus 1, this is t by 2 and this is t. So the question is the magnitudes of the nth Fourier series coefficient of W1 and W2 for n greater than or equal to 1, where n odd are respectively proportional to part A is modulus of n minus 3 and modulus of n minus 2. Part B is modulus of n minus 2 and modulus of n minus 3. Part C is modulus of n minus 1 and modulus of n minus 2. Part D is modulus of n minus 4 and modulus of n minus 2. Let us solve this problem. So in Fourier series representation, Cn is inversely proportional to 1 divided by n raised to the power 1 for fx consisting of unit steps and Cn is inversely proportional to 1 divided by n raised to the power 2 for fx consisting of ramp. So the functions consisting of ramp, the Cn is inversely proportional to 1 divided by n square. So the answer is C, because the C option is we have n modulus of n raised to the power minus 1, that is for step, and modulus of n minus 2, that is for ramp signals. Let us solve another problem. So the problem is, consider a rectangular pulse GT existing between t is equals to minus t by 2 and plus capital T by 2. Find and sketch the pulse obtained by convolving GT with itself. So basically the Fourier transform of GT is a sinc function that we know. So write down the Fourier transform of pulse obtained by the above convolution. So after performing the convolution, find out the Fourier transform. So the GT is given. This is GT. This GT is given. This is minus t by 2 to plus t by 2, and the value is amplitude is a from minus. So GT is equals to a when we have modulus of t is less than t by 2. It is equals to 0 for modulus of t greater than t by 2. So according to the relation A rect t by t has the Fourier transform at sinc of ft. So this is that draw. If we draw this signal, then it is just like sinc. It is just a sinc, means it is just following. Basically, it is decreasing. It is decreasing, and at t is equals to 0, we have at, and these are zero crossings. This is 1 by t. This is 2 by t. This is 3 by t. This is minus 1 by t. This is minus 2 by t. This is minus 3 by t. So these are zero crossings. So this is f. This is frequency domain. This is time domain. This is t. Now according to the question, we have multiplication of at sinc eft, because convolution in time domain is equals to multiplication in frequency domain. So what we will get multiplication of at sinc ft with at sinc of ft. So what we are getting finally is a square t square sinc square eft. So if we just analyze that, then we can find out that this sinc square is basically the negative area will come up. It will become negative area will become positive area if we just analyze this expression. Let us solve another problem. That is related to the Fourier transform. That is also related to the Fourier transform. So the problem is, let us solve another problem. So the problem is, So which of the following signals is are periodic? So we have ST, that is equals to cos 2t plus cos 3t plus cos 5t. Then ST is equals to exponential j 8 pi t. This ST is equals to exponential minus 7t sine 10 pi t, and the part D is ST is equals to cos 2t and cos 4t. So let us solve these questions. So let us consider the first option, that is ST is equals to cos 2t plus cos 3t plus cos 5t. So can we find out that is there any common time period? So we can find out the common time period. So the this is 2 pi divided by t1 and it is equals to 2. So t1 is equals to 2 pi divided by 2, that is equals to pi. This is 2 pi divided by t2 and it is equals to 3. So t2 is equals to 2 pi divided by 3. This is 2 pi divided by t3 is equals to 5. So t3 is equals to 2 pi divided by 5. Now t1 divided by t2, we find out that pi divided by 2 pi 3. So that is rational. And if we find out t2 divided by t3, that is equals to 2 pi divided by 3 divided by 2 pi divided by 5, and that turns out to be rational. And t1 divided by t3 is, again we find out that it is, so it is 5 divided by 2, again it is also rational. So this is periodic. So part A is periodic. Let us discuss another part, that is part B, and that is equals to ST is equals to exponential j8 pi t, and that is cos 8 pi t plus j sine 8 pi t. So that is also periodic, because complex exponential signals are also always periodic. That part C is xt is equals to exponential minus 7t sine 10 pi t. So let us draw the diagram. So exponential minus 7 pi t, the graph is this exponential minus 7 pi t, the t is equals to 0, the value is 1, and for t is equals to infinity, it is 0. So the graph is like this, it is decreasing. So we have this type of graph. So it is non-periodic. We have this type of graph, it is non-periodic. Please forgive me for my bad drawing. So this is non-periodic signal. Now the part D is ST is equals to cos 2t into cos 4t. Again it turns out to be periodic. Signal.